bit of a double act today. Do go and get the notebooks from this repository. There's also a README file in there which explains what you need to do. You only need to install the Pluto packet, well, you need to install Julia, then the Pluto package, and then Pluto will manage the rest for you from there. So we're going to be using, well, I'll say a bit more about Pluto once we kind of get into things. So the Julia programming language, it's been around for 15 years now. And it's been very exciting, I think, to see a kind of a new programming language come along and for it to develop and for people to actually start using it and for it to develop a bit of a community and libraries and actually to see it then picked up by this community, by sort of earth sciences, geosciences, and projects like Klima have really put it to good use. So I think it's kind of, from someone who's a programming languages nerd, it's kind of quite exciting to see that. So we're going to dig into it a bit today, give you a kind of high-level overview and then some low-level bits as well, and hopefully give you a good taste of it, some of the principles, and then we'll do some applications as well. So Julia is a language that's got a kind of numerical focus. It was designed by people who are from this kind of computational science numerical space, and it's really got that as its sort of primary kind of goal to be good for doing numerical computations. And I think that's where it's really thriving. It's kind of a little bit like Python in some ways in its syntax and semantics. So it's relatively light syntactically. There's some kind of things that are a little bit similar. So that makes it relatively readable. There's not kind of huge amounts of structure you have to put around things like in some other languages. But there is a big emphasis on speed in Julia as well, which we'll talk a little bit about today as well. So we're going to give you a crash course. We're not going to tell you everything. It's a 2-hour session. We can't do every single little bit of the language. Do interrupt us and ask us questions. Tianzhang knows way more about it than me, so he can field most of the questions, hopefully. So Julia, it's a multi-paradigm language. Primarily, it's imperative and it's functional. Imperative programming languages tend to organize themselves in a similar way to the underlying architecture of our systems. You sort of think of them executing instructions in order. It's sort of do this, and we do this, then we do this. So it has that kind of statement-based sort of ordering to things, which is probably very familiar to many of you in the languages that you're used to. It also builds a lot on ideas from functional programming, so where we can treat functions as data. They can be inputs to other functions. Functions can produce functions as output. We can build functions and out of other functions by composing them together and so on. So we're going to lean on that today as well. So, okay, you can write things like this. Here's our first little taste of syntax in Julia. If you were sort of in the REPL or in a Julia file, you could say x equals 2 and then do x equals x plus 1. And that'd be fine. We see this as a sequence of steps. And then we can interleave definitions inside of these as well. But we've also got this functions as first class. So here's a little taste of syntax. We're going to get more into doing stuff via a notebook later, but here's just here's a little bit of the syntax now. So I'm making a function here. That's the function keyword. The function's called make constant function. It has an argument x. And then inside of here is the definition of the function. End tells us where the end is. And the last expression in a function is the thing that's returned. Now, in this case, I'm already doing something a little bit fancy. I've got a function inside of here. So this is the thing that gets returned here. We're returning a function as the output of the function. We'll get more into this as we go on. You can also have functions that go in as arguments. So you can do something like this, apply twice, which we'll see later. You take an argument f and an argument x, and then the return result is f applied to x, and then f applied to that as well. So you can take a function as input and then use it like this. So it has this very functional programming flavor to it as well. People who've written lots of Python might be familiar with that too. So it has this focus on performance. The way it does that is by doing just-in-time compilation. So it will take the code that you're writing and it will compile it into LLVM. This is a sort of a portable bytecode which itself is then optimized highly. And this leads to the very part of how Julia achieves very good performance. And you can kind of expose little bits of what it's doing, which is really nice. We'll get into this. You can write something like this. The at symbol tells us that we're doing a macro. A macro is where we take the syntax of a piece of code and sort of do something with it and inspect it. So this code LLVM macro is going to use the JIT and then show us the LLVM code that gets produced when compiling. And okay, I'm not necessarily expecting that you know lots about LLVM, but we can see doing 1 + 2 gets compiled down into an add instruction between two registers inside of Julia. So it's a very nice tight compilation there. There's not some kind of complex objects to work with and unpack things. It gets, you know, it gets really down to code that's very close to our architecture internally. And okay, there's lots of graphs you can find online comparing Julia's performance, and you know, performance testing is difficult and benchmarking is difficult. That's what's going on in MR2 right now. But you can see there are various benchmarks of people showing that they can take Julia and get it to perform much faster than Python, even with a bunch of Python tricks and approaching kind of C and C++ performance. So the red line is Julia. Well, this is a bit old now, but this is Julia with some various things turned on, and here's the blue line is the C++, and you can get sort of similar behavior there. So this is great. This is, I think, part of why it's being successful as well, because of having good performance. And another big feature, which we're going to look at today, is its typing system. It's dynamically typed, which means that we don't have this kind of procedure running ahead of time, like in statically typed languages, checking whether it's type consistent and giving you type errors, doing that type checking. Instead, type checking happens while it's running. You look at the every bit of data comes associated with its types in its runtime system, and it's looking to see, okay, if I don't know already what the type of something is, I have to inspect that data and try and work out what to do with it. But we can put in type information into Julia as well. And that's a big part of leveraging Julia to get high performance. So if you tell it the types, it's going to be able to exploit that information to get something that is compiled to a performant code. So here's two functions. Here's an example of that type syntax. So I've got this very boring function called +int. It takes an input x, which is of type int. And so this is a type signature. I'm using double colons. That's the Julia syntax. And it says, okay, it's an int, an integer, and then it's returning x + 1. So this is going to be compiled much more efficiently than this operation down here, where we haven't really said what this could be. And this plus operation in Julia gets overloaded. You can do plus on lots of things. So at this point, it's sort of, we don't really know what it is. We're going to, the compiler is going to have to look at that x for every single time you use this function and try and determine which particular kind of plus you want to use. So these two functions will have very different performance characteristics. This one will be the fast one up here because we've declared its type. And the JIT compiler will use that information. Okay, so this is giving you little insights already before we get into more deep code. Do just interrupt if you have questions. So another part of its typing is this thing called multiple dispatch, which you might have heard. It sounds a little bit fancy. Multiple dispatch is essentially means that the Julia works out which functions you're actually using based on the types of all of the arguments. That's the multiple part in the dispatch. Dispatch is how you go from a function application to actually deciding which bit of code to use. And it has this kind of open namespace where you can redefine functions at multiple types. So I've got this function here called scale. Got two, and you can put these together in Julia. That's fine because they work on things of different type. So this scale here, it's expecting two integer inputs, and its output is an integer, and it does x times y. But then I have another kind of scale here, which says what to do if the second argument is a string, and then it does some other kind of thing. It does sort of loop where it puts together a bunch of stuff. Don't worry about what it does at the moment, but it outputs a string here. So if I'm using the scale function, then Julia will inspect the types of the arguments, and it will choose which one to do based on the types of all of those arguments. So the dispatch is choosing which function code actually applies here, and the multiple is that it's doing it based on all of the types of the arguments. So if I have two integer inputs, then it'll do this one, and if I have an integer and a string, it'll do this one. So that's, I think, part of why Julia's, one of the kind of nice things about it is quite powerful. In general, I find that languages that have some kind of overloading, which is when you can use the same function name or symbol at lots of different types, they give you quite a lot of power because you can write one piece of code that you can then apply to lots of different types, get different kind of meanings to it. So this is something that's going on in Julia, which we will leverage today. Yes?
Good way. I can also see how this can become like a debugging nightmare if you do this all in.
Yeah. You can ask Julia how it's resolved things, and you can interrogate it a bit, because otherwise, yeah, it can be a little bit tricky. You have a bit of code and you use it with one type and then use it with another, and the meaning changes. That's one of the downsides of overloading. So it's having good ways to interrogate that, which Julia does have. Yes?
Just related to that, do you have a recommended, like, have you seen this sort of overuse, this power abuse in different ways? And would you have a recommended sort of situation in which this is really the most useful thing?
So bad ways of doing overloading is to do things that are really counter, sort of have very, very different semantics under different types. So it would be like me having, and lots of languages you can do this, say in C++, you have the plus function and you can overload that to different types, but maybe you made plus do something that was just very, very different to what we might normally expect from plus. And that would be very confusing to a user because, you know, humans have context and language is based on context. So if you see plus, you kind of think, oh, I'm kind of sticking two things together. But if actually what it does is like a division kind of operation, you'll be like, oh, you know, it's going to be breaking your mental model based on your context. So I'd say if you're doing overloading, you want things that, you want operations that share the same name to have somehow related semantics. Okay. So the operator overloading leads to generalizable programming. All right, so we're going to understand some core ideas of Julia. We're going to use Julia to solve some tasks. We're going to have this sort of a look through of the basic ideas first, and then get into some application and learn how to leverage Julia's type system. So I'll do a notebook first, and then we'll go on to the simple energy balance model afterwards. So this kind of style for this workshop then is going to be a bit of a code along. We're going to have a notebook that I'm going to go through and explain things, and you can basically follow along with that as well, I hope, and sort of poke it and try and just like noodle it and do different things, and then there'll be some tasks where we can stop for a little bit and let you do the tasks. So we're going to be leveraging this thing called Pluto.jl. It's a sort of notebook system for Julia. It's a bit like Jupyter, but it has some differences. One of the things that's kind of, that I find a little bit confusing is that the results are above rather than below. Yes. Yeah. So we'll get used to that, don't worry. Now, when we have a cell, it has to contain a single expression, and we can evaluate a cell using Shift-Enter. And perhaps something that's kind of useful about Pluto maybe is that if you change a cell, then it will recompute everything that depends on it automatically. Okay, so what you want to do is run Julia. I'm assuming you've already installed Pluto. And then you do Pluto run. Pluto.run, it's a function, so we use the parentheses. And then we get this in our browser. And I'm going to choose basics.jl. So I can just do a brief pause and let people kind of get to this point. If you're stuck with something and not up to this point, please put your hand up and we'll try and diagnose it. So we'll keep going with the notebook. If you're still having trouble setting up, I would recommend just listening for the moment, and then when we go back to doing a task, then we'll try and help you get set up. But you can just kind of look at what we're doing in the meantime, or you can keep trying to install it in the background and then catch up. So I'm going to skip this beginning. This is just some setup here. We've got our first bit of Julia there. It's an expression. It's just using standard ways of writing mathematical operators, and it evaluates to 27. So this show macro here, we've just got a way of giving it a bunch of expressions. And what show is doing is giving you this little terminal printout here. This is just a way of us kind of looking at what those results are and just seeing what those semantics are of those operators. It's what we would perhaps expect. True and false are written with lowercase, and these are the sort of standard comparisons. Here we are doing a show again on a bunch of logarithms and other functions. It's showing us those results like this, and we can already see some of the multiple dispatch going on here because we've got log used with different arities, different numbers of inputs. So we've got log on the constant e here. This is natural log, so we get 1. That's this part here. And then we're doing log of 4 with respect to a different base. So that's got 2 inputs, and that's being resolved to a different function, a different functionality. So we can see that you can overload even with a different number of arguments as well. So here we have a definition. We're defining a variable, and we're defining something that's, well, might be familiar as Euler's relation. We're doing e to the I times pi. So how do we get this pi? This is nice, a little Unicode symbol. You can write \pi and then hit tab, and it converts it into the Unicode for you. So you make your code look really like doing maths. And so im is I, and we're doing e to the I pi. What does e to the I pi equal? -1. Now, it doesn't on the real numbers, but this, at the moment, is using a sort of floating point representation of complex numbers. So this expression down here is kind of testing that. Usually e to the I pi in the real space is -1. So we're saying, well, if this is a ternary conditional, lots of languages have this. It's a way of writing an if-then-else as an expression. So this is the guard of the expression. I'm looking at a Boolean. Is z equal to -1? Question mark. This is the true branch. This is what we're going to do if it's true. This is what we're going to do if it's false. And we see it's already been evaluated, so it's ruined the punchline. But it says false. Why is that the case? Well, because we're working with floating point. So we can see already that z was equal to -1.0 plus, and then this very, very small imaginary number up here. The imaginary part was very, very tiny, but it wasn't quite 0, sadly. So instead, we can use approximate sort of floating point equality, which we get by writing approx like this. And now we see that that is indeed, that said hooray, so that is approximately equal to -1, up to, sort of machine epsilon. So that's kind of useful to have if you're working with floating point. Okay.
How did you define the approximate again?
You do /approx like this.
So it's basically LaTeX.
It's basically LaTeX. Yep. Thanks very much, Pierluigi. Yep. A little memo there. Okay. So each one of these cells is just a single expression. What if we want to bind intermediate definitions, bind variables? So we can do that using this let construction, or a little let block. So here I've defined 2 variables. I've said theta, and of course that's backslash theta is ran. So the ran function gives us a random floating point, I believe, between 0 and 1. And then here we've got our z again. And so these 2 are now bound in the scope of this expression down here, and we're just showing some various standard trigonometric functions on those things and showing them. Now, the theta and this z, they belong to the scope or the sort of the region of this let end block. So theta doesn't exist outside of this thing. So if I type theta down here and shift enter to evaluate it, it says, theta is not defined. So it only exists within that block. It's only accessible to the expression down here. There's another way of doing blocks with intermediate definitions, non-local binding, which is the begin end. So here I've got something very basic, a equals 1, b equals 2, a plus b. But outside of that block, a and b now exist. So I've got a and I've got b. So they exist outside of it, but it's a way of grouping things together into sort of essentially the begin end is an expression itself. You can treat it as an expression, and that means that you can assign it to another variable. So here I've got a begin end, and I'm assigning its result to the variable which I've called 3, and 3 equals 3.
If you do a begin end in a function, does it put those variables in the global scope, or is it still within the function?
I think they're just within the function. It's a good question. Sometimes we just have to try it and see what happens. Oh yeah, sorry, I've been writing Python all morning. I don't know, just do some stuff, right? So there we go. Run that thing. Oops, sorry, I didn't want that there. Just Shift Enter, so that's 20. And then calling it Y may have been a mistake, but let's see. Oh yeah, so Y doesn't exist. So yeah, the things that you bind within a function are local to that function. Great, thanks, good question. Okay, control structures. Of course, if we want a language to do useful things, we need to do some kind of looping. So we've got a for loop, which looks kind of like lots of other languages. Really, it's working over a sort of an iterable thing. So this thing here is a range, but it gives us a basic idea of how to do a for loop. So for x in the range 1 to 10, that's inclusive of both bounds. So I'm doing print x, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 over there. Maybe I want to put some new lines in here. Hopefully this will work. Will this work, Tianzhang? Nope, because I need to convert this person to a string.
You can use print L.
Ah, no, but I want to put the string in myself.
Then you can like use string interpolation.
There we go, great. So that turned the integer into a string, and then the string concatenation operator in Julia is star, is multiply. Probably would not have been my choice, but it's okay. Worse things have happened at C. Okay, so we got the new lines in there. Okay, we saw if then else as an expression, this ternary thing with the question mark and the colon. We can write it as a block with statements in here. So if 1 is less than 2, print true. This is how you do the alternate branch, else if, and then we've got the else and we've got the end. So those of you who are Fortran fans will be very happy to have your the end keyword back. There's no end if or end do or end for or anything like that. Just end. Okay, we're doing okay. So we saw already earlier this idea of putting in types. Here I've got a function where I've specified the types of the argument and the types of the return result like this, and done a multiply by 2. Now, as we were just discussing over there in a moment, potentially you don't really want to make your function that restrictive in this kind of case. In Julia, it becomes a little bit of there's a bit of a craft about where you do and don't put type signatures, and usually the sort of what you want to do, I mean, it's nice to try and keep things general if you can, and resolve the types in the function applications, and resolve the types in the bits of data that are then going to go into functions, and let the just-in-time compiler decide for each one of the function calls what's the most specific implementation for it. But you can specify the types like this, and we can also, if I got a little thing for it, you can do things like this and specify it with that signature there. So we were already using, way up we wrote Z, that was e to the I pi, and I can query the language and ask what is the type of that thing. So I ask here what is the type of this Z, I've called that TZ, and it tells us that this is complex F64, and this is an alias for a more complicated type, complex curly's float 64. So this is a composite type, or a parametric type is another way of saying it. There's a structure for complexes, and the type of the components for the real and imaginary part can be some other type. So you can have a complex over integers, you can have a complex over floats. So these curly braces are telling us what's the type parameter for that structure. So here I've got the type of 1 plus I, and this 1 is an integer. So this is actually going to be a complex int64 instead. So we can interrogate this structure. A structure is a way of packing together bits of data together and giving it a type name. So that's what complex is. We can ask what are the field names of our type TZ. I'm kind of curious what happens if I just ask for it like this. We see that it's we've got these two names, RE and IM. The colon here tells us that this is a symbol. A symbol is kind of like a name that you can't sort of decompose. It's a name that names a field in a structure. So a structure can have names to each of its parts. You can think of it a bit like a property on an object, although Julia is not really object-oriented. So we can ask, what are the field names in TZ? And here we've got a little loop over them, shows us the loop again. And in this case, we're saying we're doing a print line. We're doing the sticking a bunch of stuff together. Print line here, we can, rather than using the star, we've got the comma to stick a bunch of things together. It's going to print those out. And then we're using this get field method, get field function, which is asking from Z for the field S. So it's a way of extracting that bit of information. We could also just type z.re and z.im directly. And that's how we access the bits of data. So this structure, it's really just a pair, a tuple of two things with this naming. And we can get at the stuff inside of it with those names. Field types, that shows us that the two components here are indeed float 64s. Primitive types, things like float 64 themselves, they don't have any field names because they're just that single piece of data. There's not some kind of internal structure to them. So I did field names on float 64. I see that that's just the empty collection, the empty tuple. There's no field names inside of that. Okay. So tuples. We're working with tuples here. Tuples are a way of sticking together a bunch of different bits of data, a bit like in Python. They don't have to all have the same type. They can be differently typed. But one of the key things that's going on in Julia is that there's immutability is the default. So in many imperative languages, when you're talking about variables, they're not mathematical variables. They're variables in the sense of they're really a pointer to a piece of memory in your computer, which means you can take it and you can change it and change the bit of memory that's inside your computer. But by default in Julia, the various of the structures are considered to be immutable, which means you can't then go and change that bit of memory. So here I'm saying T equals this quadruple, a tuple with 4 things, 1, 2, 3, 4, and I'm trying to change the first component in it. It's 1 indexed, I believe. We can always test it if we're not sure. Let's do let x equals 1, 2, 3, and x1. There we go. We should always just tinker with things if we're not sure, and if we do 0, like we're thinking we're writing C code or something, then it complains.
Can you do -1? Oh.
No. Horrible abuse of the notation here. And oh, yes, yeah, you can do n-1. Yeah, look, yeah. Yeah. All right, I'm going to hide that. I don't think so. I think that would be an out of bounds error, right? It would be a bounds error because it would go to, yeah. Well, you know, they've got a way of indexing backwards. Good, good. Okay, so we can't do this mutation. We get a method error. There's no way of us updating this tuple. It's an immutable thing. We can, if we want to compute on it, we're going to have to produce something else. We can't change that bit of memory. I'm going to skip this little while loop. You can go and have a little play with this if you like. This is just a way of us showing some things about the type structure. Is that all right if I skip this? Yeah, great. Okay, so function definitions. We already saw some on the slides. Here's a really boring function. It's the identity function. Takes an input and returns it. Identity of 42 is 42. There is actually a keyword called return in the language. We didn't use it here because we didn't need to. The expression that's in the body of a function is its return. But you can do a sequence like this and return early. So we're going to compute this in this kind of imperative, step by step. We're going to do this. And so if I do early return with 100, I get 100 and not 42. So this might be useful if you're doing some kind of control flow block, and you want to return out of the function earlier because you hit some kind of conditional. We've got some if, where in some branches you want to like return at this point. You probably don't want to write this ever. I wouldn't recommend writing this function, but this gives you a bit of an idea. Now, there are lots of fancy things you can do with functions. I'm not going to dwell on it too much, but you can do keyword arguments, you can do variable arguments, you can do positional arguments like you do in Python. So if you want to kind of go and look at that, you can go and investigate this thing here. Basically, you separate out the parameters using a comma, and these are going to be positional. And then you do a semicolon, and everything after that becomes a named argument where you have to say name equals like that. So you can see with this function, we're sort of taking a lot of possibilities here. We've got A, we've got B, which has a default value 0. We've got then arbitrary numbers of arguments that come after that. Then we can have some keyword arguments, one called C, one called D, and then a bunch of others. So if I sort of show all of these things, not sure why we have to print, but okay, and then return one of them. So we can noodle around with that and see, okay, if I pass this, the string A, is that a string or a character? Character, great. So this is like C, characters in single quotes, strings in double. So a character A, this is going to get bound to B. This is going to be in the args part. These are a bunch of variable length arguments. And then we get to this positional part, and that's going to be this C here. We skip the D, but then we've got some other keyword arguments here, and so on. So you can do a kind of, basically like in Python, you can do a mixture of positional and keywords and many things like that. That's getting a little bit into details, I think will be okay. So, as we said at the start, it's builds on the functional programming paradigm. That means we can do higher order functions. That's functions taking functions as inputs. And it has some syntax for doing these anonymous functions, also called lambdas in other places. These are functions without names. We can just construct a function as a piece of data with a single expression. So here we have one of those lambdas. The syntax is to put the name of the argument and then ASCII arrow hyphen greater than, and then the expression that's the body of that function. So this is the function that takes an input and adds 1 to it. And down here, I've made the double function. I think I called that apply twice in the slide. I'm also doing it with a lambda, but I can do a kind of mixture here. This is like a shorthand for doing this function keyword syntax. So I'm giving an argument here, f, and I'm producing a function which takes an x and applies f to x and then f to that result. So if I do double with the inc function and give it 0, then I'm going to get +1 + 1. It gives the answer 2. Down here. Here's triple, which is going to do something 3 times. Now we're using the function composition syntax. This is the sort of the backwards composition actually, but it's going to do f, f, f. It's going to apply a function 3 times. That is equivalent to us writing this. No, sorry.
Could you explain that with F, G, and H instead of F, F?
Yeah. Good question. Right, I can make compose. Let's just do it with F and G, and I'll do F. Oh, what is it?
Third.
Circ.
Yeah.
I forgot to do tab. Thank you. Right, so this is going to be equivalent to doing x, where we do g first, and then f. So it's like set theory notation. You've done the set theory. Yeah. Huh? Okay. Yes.
Is there any performance penalty to passing around functions, especially iterated functions as data, like embedded in some kind of heavy computation, like every time step of the numerical integrator?
This is a good question. In principle, it depends how good Julia's compiler is. It should be doing something called defunctionalization and closure conversion, which are sort of standard optimizations on functional programs that should be kind of inlining things and getting rid of these things. In principle, having to pass around functions can have a little bit of an overhead, but most of this should get specialized out. And I think the Julia compiler is quite good at doing that because a lot of stuff is built in this way.
So in my experience, the biggest mistake you can do is to define anonymous functions in your code, and the defining of that function will be created when you actually run the code, which is a performance hit, instead of like passing it as
Putting it
to the other function that you're actually running. But the downside of functions in general in Julia is that you can't pass in the type of the function, the types of the input and output.
Yes.
So if it's a little bit complicated what you're doing, maybe the Julia can't predict if you were to apply this function to an input, what would the output of that function be?
Yeah, there's no parametric function type, so yeah. Probably a bit beyond what we're talking about here, but it's the kind of thing where you'd want to be profiling it and trying a few different options, I think, is the way I would just summarize at this point, because it depends what Julia does. It seems like, you know, the good advice is to perhaps define your functions in the outer scope and make sure they're being passed in rather than kind of created in the middle. Right. We're going to get to a task, so I can stop talking. Here's the factorial function. It's built in. What I should show you, actually, is this. No, not that. If I zoom out slightly, is this live docs down here, which can be super useful when that's a nice thing in Pluto here. So I'm in this cell, and it says, OK, you can look at the factorial function. It tells you how it works. So nice to be able to access the docs while you're working. So we did factorial of 4, that's 24, that's great. We did factorial of 30, and we got an overflow error. This is a numerical overflow because we exceeded the bounds of 64-bit ints. But instead, we can make our factorial big function, which says, OK, if n is less than 2, then we're going to use the big constructor. This is going to give us a big int. This is sort of an arbitrary precision integer, 1. Otherwise, we're going to do n times by factorial of n minus 1. So this is going to let us use the big int representation, and now we can do fact big on 30 and get the nice result. So that's using a different type in here. It's resolving it to, well, I think this is the name of big integer in Julia.
No, it's abstract type. So it's super type of ints and big ints. Yeah.
OK. If we're not sure, check the result. Oops, what am I doing? There we go, big int. That's the type of big integers. OK, so the task is to implement the fib function to calculate the nth Fibonacci number. If you don't remember what Fibonacci is, it's the sequence that you starts with. Huh? It's in the hint. I know, but you start with 0 and 1. The next number in the sequence is the addition of the previous two things. So you get 2, 3, 5, 8, 13, and so on. So the nth one will be some position in this sequence. We could do it starting from 1 and say the nth position in fib is 0. All right, so let's have a little, you do some coding, I'll do some stop talking, and we'll go around and help if you need help.
Then you can use the methods function. Yeah. This is the dot is as like base or statistics dot mean. And so this is basically like a name in the statistics package. And the column here means is the denotes that this is a symbol. So as yeah, this is a bit weird, but let's accept it. And so as Dominic explained, you can use the methods function to get all the methods defined for a certain function. So here we can find our newly defined method here. So P is of type abstract normal, and we can also use the methods with function to find all the methods associated with a certain type. We have like the plus operator and mean, std, and var, which we defined above. So now let's implement some concrete types, which are subtype of abstract normal. So only concrete types can be constructed, and you cannot really construct an abstract type. So it's called ontype because we have no type annotation here. So if we get a few types of this normal type, both of them are any type. So any is the super type of any type in Julia, and you can construct the type using in this way. So the mean is 0 and std is 1. And we take the mean of P1 and we get 0. And we can generate samples, like 5 samples from P1. So these samples follow the normal distribution. And we can use the add which macro to find which method is called when you apply a function. So if you do this, you see that this is exactly what is called the method we just defined. And so, which means Julia must find which method is suitable for this function application. And this is based on the numbers and the types of input arguments. So as I explained before, you can use P1 as a function. You can apply it to 0, and this is the PDF of normal distribution, P1. And so it will calculate this expression here. Yeah, this one. Yes?
What's the difference between struct and abstract type?
Which struct?
Here you're using struct, normal, and type.
So any struct must be concrete type. So for abstract type, you cannot add any fields here. Yeah, so it's like a node in the types hierarchy. Yeah.
Oh yeah, sorry, we skipped a little bit, didn't we? Maybe that type hierarchy would be useful.
Yeah, I showed it. Yeah. So we can use, an important concept in Julia is called type stability, which means given a certain piece of code, whether or not Julia can infer all the concrete types of the values in this evaluation. So if we evaluate P1 applied to 0, and we use this macro called warn type, we will show all the types of the intermediate and all output values. So all of them are of the any type. So Julia cannot infer any type information in this code. And which means Julia has to prepare code to deal with any kind of possible types when executing this code. And we can use the code LLVM macro to expand the code into primitive operations and show the show the LLVM bit codes running on the virtual machine. And that's a lot of codes because the code is not type stable. So now we write a type stable version of normal by just adding the type declarations after the fields. So these are concrete types, and if we construct normal and call it apply it to 0, you can see that all the types, all the intermediate and output values have a concrete type float 64. And okay, so here we can also add two normal distributions together because we have just implemented an operator overloading here. So yeah, so we can add some newly defined types here. And if we generate the bit codes, and we can see that it's much shorter than the previous one because the code is basically converted to a statically typed code, and it's much faster like C or Java. And finally, a third example is parametric type. So we can add a type parameter in the curly brackets, and T is the type parameter, so which is the type of the parameters, distribution parameters. So if we use some other types of input like float 32, we can see that T is automatically inferred to be float 32. And so we can also check the type stability of this code. So all of them are concrete types. And an advantage of parametric type is that it can the same piece of code can handle a variety of concrete types, and this is called generic programming. So we can use vectors instead of numbers as the parameters of the distribution. And T is inferred to be vector of float 64. And we can sample from this 2D normal distribution, and it will generate a 2x5 matrix. And finally, to more clearly illustrate the advantage of type stability, we implement a function probability here, which calculates the probability that a random sample from distribution P lies in the interval between low and high. And we apply this function to all three probability distributions, P1, P2, P3, and in this interval. So this is the 95% confidence interval, and we can measure the time cost of all three codes. You can see the P2 and P3 have basically the same performance, and both of them are much better than P1. And we can also see some allocations for P1 because P1 parameters in P1 might have composite types. So for any composite type, Julia needs to allocate space. While for primitive types, it does not need allocation. So any questions so far? Okay, let's continue to the next section, collection data types. So in Julia, collection data types basically are stuff you can index, use indexing. So first one is range, like we already mentioned before. So there are two kinds of range. You can omit the step in the middle. So you have a range from the start and to the end with step 1. If you specify a step size in the middle, then you can see we can get the start, stop, and step using these fields. And so ranges can be used to index a vector. So this is how you write a vector, which is the same syntax as list in Python. And we can use this range to index v, and we'll get this result. And we can use the collect function to convert any sequence in or collection data type into an array. So a vector is the type alias of one-dimensional array in Julia. So, and index starts from 1, and we can use length to get the size of an array. So Julia arrays support broadcasting like NumPy arrays. However, you need the special dot and dot annotation to indicate that the operation should be broadcasted. And so basically applies the same operation element-wise in the array. And so now you can also use 2v as a shorthand of 2 times v, the broadcasted version of 2 multiplied by v. Yeah, so this is quite similar to mathematics. And to broadcast a function, you need to add a dot after the function name. And this will take the element-wise square root. Different from NumPy arrays, you can change the number of elements in a Julia array, a vector. So you can use the push function to add an item at the end. You can use insert to insert the item in some other location. You can use sort to sort it in place, and you can delete an item as well. Yes.
So I think if I understand correctly in Python, like say you have a code where you're gradually building a long list of numbers, and at the end you want to do like NumPy operations. So the way I would do that, I guess, is start with a list because it's cheap to append to a list, and at the end convert it to a NumPy array. Is there a corresponding best practice for Julia, or like is it fine to that combines the best efficiency with both like memory and functions? Or is a vector an array just fine?
Yeah, so in Julia there is no any kind of type like list. So Julia will pre-allocate more space for the array, so that if you insert something, it will not take a lot of time. Yeah, so I think the best practice is either you like pre-allocate the space using like this method, like this, or you can use array comprehension to construct the array. Does it answer your question? Okay, thanks. And so Julia adopts column major order, which means the elements are enumerated vertically. So if you concatenate 2 vectors vertically, the result will still be a vector. Well, if you concatenate them horizontally, it will become the result will be a matrix.
And that's the same as in Fortran, so the column major order. So Easy switch from Fortran to Julia.
Yeah.
Column major indexed by 1.
Yeah, this is different from NumPy.
Yeah.
Yeah.
I've got a little confused. So in the example above, you can change like information in the vector, but isn't Julia immutable?
Not entirely. Some structures that are immutable by default, not vectors.
Yeah, it's you can mute them in place, and so this will show how to index the array the vector using ranges. As we mentioned before, you need to use end to indicate the end of a certain dimension. You can use a minus step size to traverse the dimension in reverse order. And yeah, so matrix is a type alias of 2D array in Julia. You can write a literal matrix in this way, or you can use semicolons to separate between the rows. And we can also pre-allocate space for an array using this method. So here you need to specify the element type as a type parameter. So the onDiff basically means uninitialized value. And the rest of numbers indicate the shape of the array. So the onDiff here are just very tiny float. And then we can use a loop to assign the element values. And so here is a special syntax in Julia. You can use a comma to write a nested loop as a shorthand. So the inner loop is on J and outer loop is I. And then you can use array comprehension, and similarly you can also use the comma to separate two loops, to nest two loops together. If you don't want to nest the loops, you can use 2 for keywords, and the result will be a flat array. So you can also use other functions like zeros or rand to construct arrays. So this is an example of a 3D array, and it's printed in like this. And also you can change the collection of items where you sample the elements, and this means characters between A and Z, and it will return this kind of matrix. And here we construct a complex matrix, random complex matrix, and length will give the total number of these elements in this matrix. And to get the shape of the matrix, you use the size function, and this will give the size of the first dimension, or the number of rows. And as we said, it uses column major order. So if you get the fourth element, you first count from top to bottom, then from left to right. So the fourth element is this one. And so multi-dimensional indexing in Julia is similar as in NumPy. This is indexing the first dimension, and this is indexing the second dimension. So you can use a vector as to index as well. And then you can reshape the array. And here the column is a placeholder for a default size of the dimension, which Julia will automatically compute, just like a.reshape -1, 3 in NumPy. And similarly, you can concatenate matrices using semicolons and space.
It shows A again.
A here. Yeah, so So for broadcasting, you still need to use the dot notation, and this broadcasts the vector per column, and this broadcasts this row vector per row. And yeah, so note that there is only space in between. And so to transpose an array, you use this function. However, if you use the single quote, it means a joint operation. So it takes the complex conjugate followed by transpose. I don't know if it's the same in MATLAB or not. So you can take the sum of an array along a certain dimension or mean. So if you, without specifying the dimension, we'll take the mean of all the elements, and this will take the mean along the along each row. So to create a shallow copy, you use the copy function, and do note that functions like reshape, adjoint, creates a view of the array, original array, which share the same underlying data. However, different from NumPy, if you create a subarray using indexing, it actually copies the original data. So here are the results. So if you set one element in C to none, one element in D to none, and one element in F to none, the results, as a result, all these arrays B, C, D, and F will have 3 non-values. Well, although all the elements of E are set to none, it does not affect other arrays or matrices. So we use the add view macro to prevent the copy of the data. Yeah, so any questions so far? Okay, so now let's show some examples of generic functions for iterable types. And here AB3 are 3 different types of iterable objects. And all these functions are applicable to all of them. So one thing to explain is that we can apply sum in this way. We can provide a function as the first argument, which is equal to mapping the function to A first, then sum the results together. And we can provide 2 sequences and provide a binary operator here. This is actually the same as in Python. And we can use the zip function to zip several arrays together. And we collect the results, which means convert it to a vector.
What if we don't collect?
This will return iterable objects.
Right. A bit like Python.
Yeah. It's like this. So into like you enumerate the items. Now some tasks, exercises. So first task is to generate a 2 by 1000 random matrix following the random normal distribution, whose parameters are specified in S. And any question for this task?
Question.
Yes.
So any of these like classes, they don't have methods on them in the way that NumPy has. dot reshape and dot. The ways you got to do you got to pass an input function.
Yeah, so Julia is not object oriented. So the types do not have methods, but it uses multiple dispatch. So what you do is to overload an existing function, overload a function to create implement a method for this specific type. Yeah, so the name is in the global scope. Yeah. Yes.
Python, you make a class and tell it all the things you can do. In Julia, you make the function, then you cater to all the potential types that you want.
Yeah.
Transposed, yeah.
Not sure how I feel about that.
Okay, so let's show the answer for the first question. So we create a normal parametric instance from the columns of S, and we just sample from it to create a 2 by 1000 matrix. And can you calculate the mean and standard deviation of each row of Q using the mean and STD functions? So yeah, here this will show how to do this along a certain dimension. Okay, so the solution should be quite simple. You just take mean and STD along the second dimension and concat them horizontally using a space. So you can see the result is pretty close to the matrix S. Yeah, that's a small exercise. And finally, we like to introduce the linear algebra in Julia. Again, we create a random matrix here. And we use the linear algebra library, and it will export some functions like rank, tr, which is trace. This is determinant, and this is diagonal of the matrix. And it has a dot product as well, and also the norm, which you can specify the p here for a p norm. And it also exports a new operator, which you can type by c dot. And so I here is a special matrix. You can directly subtract I from M, or you can use multiplication or addition and so on. But I is not a concrete matrix, so it has no shape. And to inverse a matrix, either use inv or you take the -1 power of M. And so to solve a linear system, either use the inverse of M multiplied by the vector B, or you can use this special left division, which is just a shorthand of inverse of M times B. And so we create another matrix, which is not square matrix. And you can also solve this linear system by least squares. which is equivalent to the pseudo inverse of n times b. And yes, so then this will give the eigen decomposition of a matrix. And this is a structure. And so you can get eigenvalues using the values field and eigenvectors using the vectors field. And this is just a check that this is indeed an eigen decomposition. So the diag_m function will construct a diagonal matrix from a vector. And finally, singular value decomposition. And the S is the singular values. Yeah, the field S is its singular values. So we can see this also is equal to this. Okay, that's the notebook for the basics of Julia. Do you have any questions so far?
Right. Should we bring people back together then?
Yeah.
Okay. All right, folks. So, you know how it is. We spend lots of time planning a really detailed training session, and of course, people ask lots of questions, and it takes long to explain things. There's so much more to go. Tianzhang's got a lovely notebook of the Earth energy balance model to go through. We'll kind of go through as much as we can. We might have to summarize a bit, but you know, you've got it. You can take it home and play with it. It's there on the everything's on the GitHub repository for this course, so you can play with it afterwards. But yeah, Tianzhang will take us through the last half an hour.
Yeah, let's just briefly skim through this notebook.
What's the name of this notebook so people can load it up?
EBM.
EBM. So it's called two underscore EBM.
So what you do is go to the top and change the name of the notebook we're using. Because I still have the old notebook, but
Yeah, we can show them how to start.
I
think you need to go back and then
just click on the logo.
You just enter the path. So click this one, and yeah. Okay, so we're going to implement Earth energy balance model, which is really first order ODE, and we will solve it using some tools provided by the SciML organization, which stands for Scientific Computing and Machine Learning. So first, we want to download the historical carbon dioxide data from the EPA website, and the data format is CSV files, so we just use the csv.read function, and the result is a data frame in Julia, which is nicely printed here. So this is quite Julia data frame is quite similar to Pandas data frame, and you can use you can like get the last 250 rows, just like array indexing. And so we want to combine. So the data is observation data is from different sites, like Mauna Loa, which is the killing curve, I believe. And we want to take the average of each row, but neglecting the missing values. So we first replace missing values with non values and take the non-mean, and we get a time series, two columns, one is year and one is CO2. So we can plot the curve here and using the plot function, and we want to fit a cubic curve. So we construct a matrix of the linear, quadratic, and cubic features of the time, and we use least squares to find the coefficients in this polynomial. And you can check the coefficients here. Yeah, so this is the coefficients of the polynomial, and it can be plotted here, and which is quite nicely fitted. And the reason why we want to fit this curve, because this allows us to predict into the future. So because it's necessary to solve the ODE using, so we cannot use the historical data to solve the ODE. And so a brief introduction to the energy balance model. 3 major components. First is incoming solar radiation, which is a constant. And the first is outgoing thermal radiation, which is a function of the temperature. And here we want, since it includes feedbacks and so on, and very complicated, we use a linear model to approximate it. And finally, finally we have greenhouse effect, and this is the forcing term in the ODE. So empirically, it's a logarithmic function of CO2 concentration. And so the model is, the construction of the model is from these 2 sources. And we can use the differential equations and modeling toolkit libraries to build an ODE system. So this is the constant term of solar radiation, and the change rate of temperature is a linear combination of these 3 terms. The G is the outgoing thermal radiation, which is specified here, and the greenhouse effect is the log of R, which is the ratio of CO2 concentration at the current time and the pre-industrial time. So now we have a system of 3 equations.
What exactly does the at parameters and at variables do then?
So parameters are constant variables in the ODE system.
Symbolic.
Yeah, symbolic. And variables are like variables that depend on the time t. T is in the parameter. So not really constant, but like independent variables. And these are the dependent variables. So we use the ODE system with the MTK build macro, which is the model toolkit build. And now we have the ODE system, like plotted, displayed in the LaTeX math mode. And to convert the ODE system to an ODE problem, we need to specify the numerical values of these parameters and provide the initial condition. So, and also the time span of the ODE. So, yes, so T0 is the global average temperature at the pre-industrial time, which we assume is at thermal equilibrium. And these are values for the parameters. So we can use the solve function to solve the ODE problem. And the solution is printed as a data frame, but it's actually can be applied as a function. So if we apply it to a certain time period, we can give the predictions of the model. And now we can plot the function, plot the ODE prediction. So the reason why we need the CO2 function, because it will provide the CO2 concentration in the future. And So we can see the trend of warming. So now to compare it with the observation data, we download the data CSV data from NASA and do some processing. So the result is also a time series of temperature. And we can plot them together like this. So the model prediction is not really good, but it shows some of the trend of similar trend. So the reason why the predicted temperature is first higher than observation, then become lower later, is probably because we use a very simple linear estimation of the outgoing radiation. So let's use a neural network to approximate the second term, which is the outgoing radiation or the climate feedbacks. And we use Flux, which is a deep learning library in Julia, and replace the linear climate feedback. So to do this, we use symbolic substitution. We define a new symbol variable GNN. So it is the approximation of the neural network of G, and replace the original G term, and we substitute R with the formula defined in the third equation, and then we simplify the right-hand side of the first equation, and we get an expression of the new change rate of temperature. So in this way, as soon as we input the output and the time, we will give a numerical result of the change rate of temperature. So let's build a neural network here. First, we set the random seed to ensure reproducibility, and the Flux neural network is simply concisely written here. We use SELU as the activation function. This is the dimensionality of the hidden layer, and we use a custom initialization function called chi-mean normal, and so we use the destructure function to obtain the vector of all parameters in the trainable parameters in the neural network, and then also a reconstruct function. So given the vector of parameters, the reconstruct function can output the neural network with the parameter values. So the NN term is used to substitute the GN term in the neural network in the ODE. So we will do some feature processing of the ERT and input the linear, quadratic, and the cubic of time, and we'll get a 2D result, and we'll make it a linear combination. So just a linear function of t. So then we define the function which uses the output to output the change rate of temperature. So here we just substitute the GN term with the net output of the neural network and the t with the current year. So, and we build it into a ODE problem with the same initial condition, same time span. Only the parameters now become the neural network parameters we obtained here. And now we train the neural network. We get true temperatures from the observation data, and we make the prediction by solving the ODE problem, neural ODE problem. So the mask is to select the years where we have observation data. And the loss functions is defined as the mean square error between the prediction and the true temperature. And we use Adam optimizer and use the flux.train function. So we provide loss function, the neural network parameters for the optimizer to optimize the data, which is generated here, and the optimizer. So we can see the loss, training loss. And so we have two phases of training just to accelerate the process. Because after 100 epochs, the learning rate becomes very small. So we restart it with a new optimizer. And this is the second phase of the training. And at the end, we get an average error of about 0.11 degrees. And we can animate the process using the add-give macro. So we have a for loop, and in the for loop, we just plot a separate, we just generate a plot as the frame in this animation. And yes.
What is the difference between plot and like plot with the exclamation?
Plot?
Plot and plot exclamation mark.
Yeah, so the plot will generate a new plot, and this will write the data into the current plot. So the title will add a title in the current plot. And so the ban character after a function name usually means it will modify some of the arguments in place instead of, so it has some side effects, but it is only a naming convention. And we plot the final results here. So by substituting the long wave radiation, which we linearly approximated with a neural network approximation, the prediction is much better than the previous one. And so we can see that by 2050, the temperature is about 2 degrees higher than the pre-industrial level, and which is very bad, I think. And and we get a figure from the IPCC AR6 report for reference. You can see that even with intermediate emission scenario, by 2050, we will also get warming for about 2 degrees of 2 degrees, and which is in accord with the prediction of the model. Our model is in accord with their prediction. And okay, so we have some further readings. This is a cheat sheet of Julia language and some other articles, and a take-home exercise, which we can show the result. Oh. So this is the long wave radiation, outgoing radiation in the original ODE, and this is fitted by the neural network, so it becomes much more complex. And this is why the performance is better. Okay, so questions?
Got some pretty funky behavior, hasn't it?
You mean the neural network?
I mean, that period 1890 to 1920 was very.
small. Yeah. But so just to recap, you sort of solving your ODE with a given set of input parameters, and the machine learning is working on those input parameters.
Yeah, so we replaced the ordinary ODE with replace one term with a neural network approximation. Yeah. So, any other questions? Or about the basics notebook? Any questions about this notebook? So, shall we finish? Huh?
BBM is a very common.
Thank you.
Extension that you can add button that goes with like best practicing for example. Is there any similar things for Julia?
Yeah, so there are some guidance like Julia Blue, I believe. No.
Homework is to go watch that movie.
What? It's not called Blue? Yeah, for example, you can check this page here, style guide. So for some best practice of Julia programming. Okay. Yes, I think there is also some packages like Black that can automatically reformat your code. But it's not called, I'm not sure its name.
There is apparently there's a VS Code extension for Julia to do formatting, but
Blue style.
Blue.
We use Julia formatter.
Okay.
Is it good?
Yeah. It has basically the same as like reasonable basics, and then the same as the back is called in Python. You can change the length of the lines in the format.
Of course, that's specific to VS Code. So if you're a Vim or Emacs user, then you're
Oh no, that's just a Julia package.
Oh, it's a Julia package.
Yeah, so we run it on CI.
Okay, oh, that's cool. Oh, nice. Oh, that's much better then, yeah.
So is there an equivalent like rough in Python? Is there a Julia equivalent of rough in Python, like in Python?
Julia format package.
So not only code format, but also like LinkedIn or MyPy stuff. I don't know. Yeah. So I think we can wrap up now.
Yeah. Okay, right. So I think that's a wrap. Obviously, there's lots of stuff there for you to go and stare at and play with on your journey home. Hope you enjoyed that. Do let me know if you have any questions. You can ping us on Slack later. So yeah, thanks very much.